Yeah, welcome to module 2, lecture 1. In this module, I will discuss about the analysis of converter circuit, and in this converter circuit then we will go for the modeling of equivalent electrical circuit, so that we can analyze the complete HVDC link. So, before go for this analysis of converter circuit, it is important let us see the simple analysis of rectifier circuit, and then we will see what are the desired features or requirement for the converter circuits that can be used for HVDC application. So, in this rectifier circuit, let us see the various assumptions and their justification that which I am going to make. So, first assumption is this AC source has no impedance. It is believed that the AC source which we are using, it is a perfect sinusoidal, and also the frequency is constant. Normally, you know, the generation is a balanced circuit and it is a perfectly giving sinusoidal, and also the frequency is constant. So, for all our analysis, we will take the voltage of the source is a constant voltage as well as the constant frequency. If you are taking the polyphase circuit source, means we will go for the three phase circuit analysis for the converters, then we will assume that it is a balanced voltage, means all three phases are balanced. And you know, the balance means your all the three phases magnitudes are equal and they are displaced by 120 degree, and it is in clockwise, means they are displaced by 120 degree. Means here if I want the balanced circuit, means we are having EA phase, A phase, here it is EB, here it is EC. So, they are displaced by 120 degree, and it is your, if you draw the phasor diagram, it is your EA, here it is your EB, and here it is EC, means it is in clockwise direction. Another assumption regarding the transformer, it is believed that it is a ideal transformer, means it has a no leakage impedance, means there is a no drop across the transformer, and its exciting admittance is also negligible or 0, means it is just like an ideal transformer, and even we will also not consider the resistance of the transformer, means we will assume this is an ideal transformer. However, if you are going to take the your practical transformers, it will simply drop some impedance, means it will, due to the current flow, there will be some loss as well as some drop in the inductance will be there. But for our analysis purpose, we will take this transformer is ideal one. The third assumption is your DC load has the infinite inductance, means your the DC current is constant, means it is a ripple free, but the voltage will have pulses, it is not ripple free. Means I want to say that here if your current is a perfect DC in the output, here this is your DC current, that is your ID, it is a constant, it is a ripple free. However, your output voltage, it is not ripple free, and we will see later on. The last assumption that I am going to make, we are assuming the valve is ideal, means it will offer the 0 resistance during the conduction phase. Means once it is conducting, it will offer the 0 resistance, and once it is in off condition, then it will offer the infinite resistance. 0 resistance means it is also lossless, means there is no loss in the valve as well. Let us see some definitions which will be used even though for the further analysis. First one is the rating of valve. The valve rating, you know, the valve here I mean it may be a simple thyristor, it may be a GTUs, or it may be combination of thyristors or GTUs. So, it is a complete valve, and normal rating here, normally we say that the thyristor or valve rating is your voltage, current, and its power rating. Here this voltage rating is nothing but it is the peak inverse rating, peak inverse voltage that is appearing across the valve. This power is nothing but it is your the peak inverse voltage. We will discuss what is the peak inverse voltage across this valve, and then multiplied by the I average. It is not IDC, it is the average voltage which is appearing across the valve. This is the average current multiplied by peak inverse voltage, and the peak inverse means the negative side, what is the maximum voltage appearing. You know, the forward voltage is always 0. Once it is conducting, so it will be 0. So, we go for this peak inverse voltage, and the current here, the current rating is its maximum, the current which is flowing through this valve. So, the volt ampere rating here is the average current multiplied by the peak inverse voltage. However, the voltage rating is your peak inverse voltage rating. Your current rating is maximum current which is flowing through the valve, it is the rating. So, the peak inverse voltage PIV, which I will be using continuously, is the peak voltage occurs across the valve during the non-conduction state or phase. You know, once it is conducting, as I said here, once in the conduction, V conduction, the valve will be 0, and then we have to see non-conduction state, and it will be the varying instantaneously, but we are going to see what is the maximum voltage in the non-conduction phase. Another will also see the rating of the transformer. We use the transformer from primary to secondary and then converter is connected. So, the VA rating of the transformer is the product of RMS voltage multiplied by the RMS current. Now, you know, in transformer, the primary RMS voltage multiplied by the primary or RMS current will be equal to your secondary RMS voltage and RMS current, because the transformer, the primary VA rating will be the same as the secondary VA rating. So, at any side, if you are going to calculate what will be the rating of the transformer, it will be your RMS voltage, simply I can say, multiplied by your RMS current. So, the transformer rating here again we go for its V, that is the maximum voltage it can sustain. Again, it is going to be primary side or secondary side. So, I can say it is Vp over Vs. Then we go for the power rating here, and this power rating is nothing but your Vrms multiplied by your RMS. If you are considering the primary side, then it is a primary RMS voltage multiplied by primary RMS current, or if you are considering secondary, because this primary side power will be the same as your secondary side. And we have assumed it is an ideal transformer, so there is no losses, so both will be same. And then another term which will be continuously used is a pulse number. Normally, it will be denoted by small p, and the pulse number of a converter is the number of pulsation per cycle ripples of the DC voltage per cycle of AC voltage. Means per cycle of AC voltage, how many the pulses or ripples or pulsations that is going to occur in the DC side voltage, and that is called the pulse number. Well, again with examples we will see all the terminology again. Now, another term which is slightly tricky, and why this is used, and this is called the commutation group, and normally it is denoted by Q, and it is defined as a group of valves in which only one valve conducts at a time, neglecting the overlap, is known as a commutation group. This will be more clear when I will be discussing about the three-phase converters, and this Q is used to generalize our topology. What will be the best suitable your converter configuration, this Q will be used. To realize it, you can see the equation which is written, the P, that is a pulse number, it is equal to your Q multiplied by S is multiplied by R. Here the Q is nothing but is the same commutation group, and then your S is defined as number of series valves, and your R is number of parallel valve in a converter bridge. So, this pulse number is basically multiplication of the three quantities, and we will see what should be the optimal value of Q, S and R that will give the better performance of a converter circuit, and we will analyze later on. Another term will be also used, that is a VDO, and that is nothing but it is the average DC voltage of the converter terminal when the delay angle is 0. Delay angle, if you are using thyristors, GTUs or IGBTs, you can delay in your firing, and that is normally it is called delay angle alpha. Alpha will be used very commonly here in our analysis as well. So, VD is the D denotes your DC, and O denotes your the delay angle is 0. So, VDO is the DC output of your rectifier or converter circuit when there is no delay, means we are firing at the 0 instant. Now, let us see a simple, already you know it, half wave rectifier circuit, and we are considering a single phase of course here, and it is a very simple circuit, and it is called half wave because half of the wave we are getting the output voltage is same as the instantaneous voltage, whatever we are here, that will be appearing here, and the remaining half of the cycle it will be 0, because this will be in the reverse biased. In this case, only problem that we cannot get, even though you are putting here inductor circuit to make the DC current ripple free, but it is not possible in this case, because half of the cycle it will be 0. So, that is why here written the current is inherently intermittent, means it is varying, and thus DC current cannot be the constant in this case. So, we will see if you are going for this full wave rectifier, that is possible that we can have the constant DC current, but in this case we cannot have, and again we will see its output and other things. So, DC current and your voltage pulsate at the same frequency at the AC voltage and the current, and if you will see its output here, you see this is your applied secondary side voltage, where it is the EM sin omega t, and what is your output voltage, instantaneous output voltage here, that is varying a first half cycle when your diode or thyristor becomes positive, and then we are getting here if the delay angle is 0. So, then we are getting here the complete cycle, and other cycle it is 0 because it is in reverse bias, and then similarly here. So, this is the instantaneous voltage which is appearing the output of this rectifier circuit, and if you are going to calculate what will be the average voltage, that you have to just integrate over complete cycle. Here you can see the pulsation number, the pulse number is unity, because it is in one cycle here we are getting only one pulse of the DC output. So, the number of P in this case is unity 1. Another very important factor here, I have written the voltage across your valve or your diode or thyristor, whatever you can call. So, here it is a valve voltage. This is very important when we will go for this analyzing the converter circuit, because this decides the rating of your valve, or you can say that individual valve here. So, this is called the peak inverse voltage, and this V here it is nothing but V 1 here I am writing, this 1 denote this is the voltage across the first valve. In this case only one valve is there, so it is the V1 is denoted. Later on we will see when we are going to use the 2 valves, then the V1 V2 will be used. If you are using 6, then it will be V1 to V6 valve voltage. This is nothing but it is your E1 which is just applied here minus your the instantaneous voltage Vd. So, this is the valve voltage, and the peak value of this is known as the peak inverse voltage, means it is your peak inverse voltage in this case will be nothing but your EM. If your supplied voltage of secondary side, that is E1, it is I am writing here EM cos omega t, or you can take sin omega t. In this representation I have taken it is sin t. So, this is your V1, that is the voltage appearing across the valve during the complete your conduction as well as non-conduction state. Once, as you can see here, once it is a conducting, here this voltage is 0, because we have assumed it is a ideal valve. Only during the non-conduction phase here, this minus this, you can see we are appearing here across the valve. Now, this basically circuit again, I want to say that this is the very simple, means the simplest rectifier circuit, and especially used for the very small power applications. It is not used for the large power applications. The DC output voltage here can be calculated. You can see here, as I said, only you have to take the average voltage across what is this in this upper cycle. So, here in this portion you are getting the some voltage, here is a voltage 0, and this is a complete cycle. So, we have to take the average, or we can just take this is a 0. So, we can go to take this average, but we are integrating over the complete cycle, and with this expression we can calculate what will be the DC voltage. You can say it is divided by 2 pi, because we are talking about the it is again regular and the pulsating output voltage. So, the 2 pi here, but from here 0 to pi I have to consider, because you know is a positive half cycle only appearing, remaining is 0. So, it is a Vn sin omega t differentiated with the d omega t. One of the major what people get confused here, normally while integrating they go for the dt rather than d omega t, because once your wave it is here, either you are writing in theta or you are writing in omega t, because this is we are writing in the radians or in the degree. So, your differentiation will be also this d omega t, here omega t is theta simply. So, it is nothing but is the Vm sin theta d theta. It is not dt, because later on we will see if we are doing some mistake, then it will be giving different result. So, here we are integrating, and finally, we are getting the output voltage or average output voltage is Vm, that is a peak voltage divided by pi. I think here in our sinusoidal represented in the figure, it is Em. In this case, Em and Vm is same, means here your Em is nothing but Vm. So, we can see here the peak inverse voltage already in the figure, just we have seen here the peak inverse voltage is your Em, and the pulse is unity, and your the DC output voltage here, DC output voltage is your Vm upon pi. Now, another circuit that is called full wave rectifier circuit, again we are considering for the single phase. It has the two valves, because we have the two here, you can see the first and second, that is denoted by V1, and the V2 means it is a voltage across this is V1, means this we are taking the positive side. So, this is your V1, this is your V2, means valve 1, valve 2, and it has the two valves this circuit, but this the transformer we are having, it is a just a center tapped secondary transformer having the turn ratio T this side is 1:1 here. Now, in this case here we are using a large inductance to make our DC current constant ripple free, and we are having some loads here, and again we will see the difference here, this E1 and E2 are in the phase difference of 180 degree. Here if there is a positive here is appearing, so here it is a positive, here it is going to be a 0, here going to be negative. So, both E1 and E2 in the phase opposition, and from this voltage wave shape you can again see it. Now, you can see in this diagram your E1 here it is going to be positive here, we have taken the 0 axis here, or you can take anywhere here. So, here is E1 is positive, but E2 is here is phase 180 degree. So, this is the E1 is varying, here your E2 is varying. So, the output voltage you will see in the circuit, this is for this your E1 is positive, means your first valve is conducting, and in the second here your E2 is going to be positive, your second valve is conducting, and E1 means valve 1 will be offline. So, you can see here in one of the cycle here we are getting 2 pulses. So, number of pulse is 2, and only here we have assumed this IDC is the constant. Now, in the second figure, this Vd is the voltage that is appearing across the load, this after inductor. So, your inductor, this shaded portion is the basically the voltage that appears across the inductor, means in the circuit again you can see here your Vd is here, this V capital V, that is the DC voltage here was appearing here. So, the difference voltage is appearing here, this is the instantaneous voltage which is coming just output of your rectifier circuit, and this voltage again will be this E1 minus your Vd will be appearing across this, and this voltage here your E2 minus Vd will be appearing across the V2, that is the valve voltage. Now, here only the difference here you can see the major difference from the previous case, the valve, you can see the peak inverse voltage in this case is coming the twice of the voltage of the secondary side. In earlier case which is a half wave, it was the peak inverse voltage was only Em, and now it is twice of Em. Why it is happening again is as per definition, you can see from this circuit here, what is this your voltage, this is your Vd, this is a curve of your Vd. So, the voltage the peak inverse voltage, let us suppose you want to see across the V1. When this here E2 is conducting, means V2 E1 is off. So, this is the voltage, this minus this. So, now it is a minus of the 2 E2, because this E1 we are talking once here E2 is conducting, means voltage again we have to see here the V1 is your, now in this case it is your is E2 minus Vd. This no E1 minus Vd, always it will be E1 minus Vd. So, here this is E1 minus Em sin omega t, means at this it is Em, and now going to be difference of this. So, this is going to be minus, so it is a twice of this. Similarly, we can calculate for your another circuit, means another valve. So, you can see here the ripple is 2 and your peak inverse voltage is going to be twice of your peak voltage, that is of secondary side. In the current, if you will see the current which is shared, now the current, it is once it is your, in this case is a positive voltage, your this means valve 1 is conducting. Once valve 1 is conducting, it will carry complete the DC current ID, you can see. During this period, valve 1 is conducting, so we are getting the DC voltage. DC voltage is coming, and this I1 here, the current is complete carrying. However, this if you will see the I2, it is off condition, it will be 0. Similarly, when your E2 is becoming positive, valve 2 is conducting and valve 1 is off. So, this is your current is coming here. So, this is the current which is coming in this your the secondary, that is I1 and I2, but if you see the primary current, it will be here this ID by T, because we are taking this, in this case it is by T, means it is the turn ratio we have considered. So, in this case we can see the voltage which current which is appearing across the primary binding, it is not a sinusoidal. It is just like a pulse. Here I think here it is not seen, but the current in the primary side, it is going to be this, it is going to be here, and like this, it is just like a pulses, it is not a sinusoidal. That is why in the DC circuit, here analysis in the converter circuit, always we are not getting the perfect sinusoidal, we are having a lot of harmonics, but the fundamental having the highest magnitude and other harmonics will have the minimum. But and that is why our transformers are designed a special way, so that there should not be any saturation and losses should be minimum, because there are so many harmonics are entering the transformer. Similarly, if we will go for more larger and larger phases, we will see this will be almost perfect sinusoidal, and we will analyze for the 3-phase circuits. To see this average voltage which is going to appear across this output of the your rectifier circuit, here since it was pulsating twice in a cycle, we can take the average of one pulse only, and then it means it is a cyclic. So, here that is why it is averaged over pi, and we are also integrating from 0 to pi, and here it is a Vm I think we have taken in the figure, it is Em, both are Vm and Em is same, here sin omega t d omega t. So, if you are going to integrate, now you are saying this output DC voltage becomes the twice of the half wave rectifier, that is a 2 Vm upon pi, and but the problem here is the peak inverse voltage of the valve becomes twice of Vm, means you are going for the double of rating of a single valve. Now, you can imagine here, no doubt the pulse number is 2, but we are going for the 2 valves, and but the peak inverse means rating is going to be doubled. But if you will see the average current is going to be reduced, and it is ID by 2, and if you are going to multiply the rating, you will see the Vm over ID. So, the rating of the valve becomes Vm, that is peak voltage multiplied by here, but the voltage rating it should go for the twice. There is a consideration that the power rating is same, but the peak inverse voltage are different. For example, same you can see here, let us suppose here the voltage rating is your Em, the current rating is your ID, because the maximum current which is flowing, and your this value the peak inverse, in one case it is your Em into ID by 2, in another case maybe it is ID. The power rating of a rectifier valve may be same, but this rating can change. So, the cost of that valve will be more, is a twice of this, because the voltage rating is very, very important. So, if you will see, if you will go for another configuration, then people say it is better to go for another configuration. Also in this case the transformer is not utilized properly. So, it was suggested that we can go for your bridge rectifier circuit. In this bridge rectifier circuit is almost same, only you will see here in one phase here the two valves are there. In another, if you are reversing here, the two valves are conducting, means it is your transformer is basically used twice in the same cycle, and that is why the utilization of this transformer is better, but we are going to have the 4 valves in this. It is for single phase again. We are going to use 4 valves and one transformer having the tap ratio here T is to 1, because T I am denoting because in the wave shape we are using the T. So, in this case the major advantage is that we are having the better utilization of your transformer, but the number of valves are increasing. To see here again this wave shape here, now this is your secondary voltage that is appearing. This I am assuming as a 0 axis, because it is a continuously changing, you can have your axis anywhere in this. So, you are just taking here the sinusoidal voltage of one cycle. Now, taking as a 0 axis here, you are getting, let us suppose Em sin omega t, your this value is your that is appearing in the secondary of this your bridge rectifier. Now, here you see that there the 2 valves are conducting in that pair, and especially as per numbering which we have denoted here, your in the first way it is your valve 1 and the valve 2 are conducting, means it is normal in such a way that in the positive half here this is going to be positive, this is conducting and your current is flowing here and it is going back. So, your valve 1 and 2 are conducting during the positive half. Once this is going to reverse here, now this voltage here your this is going to be conducting, means your 3 and 4 are conducting and we are getting the output voltage. Means in one it is the 2 valves are conducting at a time, and you can see here means again in one cycle, once in a positive cycle we are getting this is your output voltage, means here your 1 and your 2 are conducting, and in the another cycle here your 3 and 4 are conducting, and this is your Vd is showing your instantaneous output voltage. Now, if you will see this the valve voltage which is going to appear across the various valves, let us suppose valve 1, in this case your valve 1 and 2 are conducting, means the voltage across valve 1 is 0. Now, here the valve 1 and 2 are off, and the voltage here we have to now see it is not directly from this minus this. If this minus this you are doing, you will see it is twice of this, but here V1, and that can be again analyzed by this circuit in the basic circuit. You can see why it is your. Now, you can see here this is your off during the half cycle, means your this is conducting and it is going to be this. So, the voltage across this is the voltage, means voltage across this is this voltage minus this voltage, no doubt, and here you will find this voltage across this is only Em, means just you have to this voltage VDC Vd minus your the reverse of this you are subtracting, this voltage is going to appear, and this voltage is nothing but your simply Em, means my peak inverse voltage. So, compared to the previous circuit, the peak inverse voltage in this case is reduced by half, but number of valves are increased by twice. So, what happens here? You can see the number of pulses are again same, but only the peak inverse voltage here which is going to appear, it is your Em, or here just I am writing here Vm, and if you will see the rating of the valve rating here is reduced by your 0.5 here this. Now, if you will see the cost wise comparison, this is no doubt it is reduced by half, but we are going to use 4, but this value is reduced by half. So, in this total circuit configuration, if you find this is the cheaper option compared to the previous, because in that case it was twice Vm and this was the point double of this. Now, you are going to use 4. So, it is the same, multiplied by 2 it is the Vm Id, because the average power here again Id by 2 and you are going to be this your peak inverse voltage is this. So, the rating of your thyristors or your valve is reduced by half in the voltage sense. Power rating, if you are going for 4, it will be up. Now, average voltage, as I said, it is again the 2 pulse full wave rectifier. So, the average voltage will be also 2 Vm upon pi. You can just calculate, because we have taken for one cycle only, not one cycle, even half of the cycle of AC, and it is since pulsating twice. So, we have just average over to pi and we can get it here. We will see in later stage, taking the average output DC voltage, taking sin omega t is not convenient. You know, is any signal here you are taking average, let us for this signal you want to take the average of half of this. One option that you can integrate this from here 0 to let us suppose pi, and then you are taking sin of this. So, this signal average can have whatever the value here you are having. Here we have taken the Vm, here it is a Vm. So, I can say it is a 0 to pi Vm sin omega t d, and going to take 1 over pi. Another option is that we can shift our axis and we can take from here the same be equal to this 1 over pi minus pi by 2 to pi by 2, and here it is your Vm cosine omega t d omega t, both are same. What happens here, our axis is shifted here and we are integrating from here to here, means the same wave shape we are doing in this another way, and we will realize later on this option is better for calculating the DC output, because you know the cosine integration directly becomes sine, and once you know sine value 0 to pi very quickly, otherwise cosine value it is going the second coordinate, it going to be negative 1. So, this option will be very frequently used when we will go for the 3-phase circuit. In the single phase you can either use this or use this, it's both complexity is almost same, but in the 3-phase we realize this is the very convenient option compared to your single, this is a sine wave. So, here as I am using here, but we will see later on we will use the cosine, and again our only we have to change our integration limits and other thing will be same. So, in this circuit we can see, I can say here in the peak inverse voltage is halved, and this circuit is basically very widely used for high voltage application. You know why it is high voltage application? Because your peak inverse voltage becomes only Em. If you are going for this your another circuit full wave rectifier, it was the 2 Em, and there is a possibility that you cannot get your valve of this such a high rating. So, the bridge rectifier single phase is used for high voltage application, where the peak inverse voltage is one of the limiting factors. But if you are going for high power application, even though the previous full wave rectifier is also sufficient. Another here advantage, as I said, in this circuit, in the single phase your bridge circuit here, this your transformer here which going to be properly utilized. So, this is also a consideration while if you are going to analyze any circuit, what is the utilization factor of this transformer. So, in the later phase when we will go for our analyzing of the DC rectifier, what should be the optimal configuration, this is the our main consideration that we should have the maximum output voltage here for the same given here your sinusoidal EMF, and your transformer must be utilized properly, and the peak inverse voltage of the valve should be the minimum. So, these 3 criteria for any converter circuit is normally used, means we should get the maximum output, we should have the minimum peak inverse voltage, and the transformer should be the properly utilized. With these conditions we will see when we will go for the actual 6 pulse or 12 pulse rectifier circuits or converter circuits. We will see with this consideration, and then we will see what should be the configuration, and finally, we will find the bridge converter is the best option with some slight modification. So, in this, if you will see the current, as I said, the current through the valve here, valve 1 and your valve 3 is the same once your this is valve 1 and 2 is conducting, and it is across your 3 and 4, it is this when your second half, it is means when 1 and 2 are off, means it is going to be a 3 and 4 valves are conducting. The primary side, the current you can see here, this is the primary side current, in this case it is a pulse. Another difference with the half wave rectifier circuit, you can see the secondary side as well as the primary side is same. Means you can see here I s is equal to the T multiplied by I p, means T is the turn ratio. If the T is unity, means I p is equal to I s, means primary and secondary I am talking. So, this configuration here you can see it is a complete square wave in the primary as well as the secondary of this transformer. However, if you will see in our previous circuit, it was here you can see in this circuit, this circuit only it was primary was this, however, the secondary was either this one, because we are having the two transformer center tap, one was here, another was here. So, it was not a perfect, it was having some DC current as well in the secondary of the transformer. However, in that case we are the DC is 0 and we are having no doubt harmonics also here we are having, but the primary current is complete square wave, means DC value is 0, but the secondary currents having some DC values, and that is why it is more lossy. So, there are so many, if you compare your bridge rectifier circuit and your full wave rectifier circuit, this is a better. This is a good question. Here I am assuming that transformer has no leakage impedance and it has a very minimum exciting admittance. The no leakage here I am considering only for analysis purpose, but let us suppose if you are having the highest, means more leakage impedance, what does it happen? It only reduce the voltage of your secondary side, nothing else, because there will be drop in the leakage, and that leakage drop will reduce your this value, this instantaneous voltage will be reduced by certain factor, nothing else. But for analysis purpose, because we are taking very easily what is your primary side and secondary side, so we are not going to consider the leakage impedance of the transformer. But no doubt here the actual transformer is designed in a such a way that it should have the large leakage reactance, because when there is any short circuit in the converter circuit or maybe in the DC side, the current will flow through the transformer and it should limit it. Especially during the converter fault, this transformer is the only the safety measures or safety valve for protecting the your valves. So, in practically we should go for the large leakage impedance, but analysis I am taking as a 0, because we are assuming so only the your secondary side voltage is transformed that by the turn ratio, and that is appearing across your valve, nothing, this is no difference. Now, we are, let us go for this 3 phase, because single phase this I analyzed. Here is your 3 phase rectifier, and this 3 phase rectifier, it is a very simple one way rectifier. Here having your the 3 valves, means this is your delta star connected transformer. Here it is in delta, turn ratio in the phases per phase transformer, it is a T:1, it is from this phase to this phase, and here it is the neutral is allowable, and this it is connected to the neutral. So, we are having the valve 1, 2 and 3, they are connected in phase A, B and phase C. So, here this is the continuous firing of the valves. When valve 1 is going to conduct, means your valve 3 was conducting, and then valve 3 will come into the picture. Then valve 2, then valve 3 and so on. This will be is a complete cycle, it will be keep on conducting. In this case also, here we are assuming the DC current is constant, that is the ripple free, and the voltage across this DC output voltage, it is instantaneous voltage. Small quantities are representing the instantaneous value, instantaneous quantities, and the capital it is showing over the average or DC values. So, this ID is shown as the DC current, which is a constant. It is instantaneous as well as the constant value, but the output voltage here we are measuring, that is a VD, which I am calculating here. This is your average value, and that is integration of this VD, nothing else. To see it again, let us see the wave shape of this. It will be slightly complex, as that is why I start with the single circuits, so that the single circuit looks very simple. Now, we are jumping in the 3 phase. That is why it was my motive to start with the single circuit. Directly if I am coming here, you will say what I am doing here. So, it is better to now analyze what happens. We are taking at here at the 0 axis. Now, in the circuit here your this EA is going to be positive, because your EC is going to be here negative. At this point your EC and EA is equal, means now once your EA is going to increase, and means your valve 1 can be fired, because the condition of any valve that can be ignite, can be go in the conduction mode if it is having forward bias. So, at this point you can see EA is more than your EC. At this point it is equal, means this, even though you are having a gate pulse to your valve 1, it will not conduct. We are assuming your valve 3 was conducting. Valve 3 means EC voltage was appearing across your output, and at this point we can, if we are giving the positive pulse to your valve, this will conduct, because the voltage across this is going to be positive, and valve 3 it is going to be negative. So, what happens here? We are, as said here, we are assuming there is no delay right now. We are assuming it is a perfect diode. So, here it can ignite, your 1 can be conducting, and once 1 is conducting, your output voltage is becoming EA. I think this previous slide showing your the circuit, but once we are going to analyze this wave shape, it will be important that we should again see here. What happens, as I said, this your EC is here, this is a conducting, means your the value here is coming to be your EC. Now, this voltage across this is your EA minus EC, and once it is going to be EAC, means always if you are writing this EA minus EC is basically voltage which is appearing across your valve 1 all the time here. During that conduction phase, here it is going to be your this, but it is every time once this is conducting, the voltage across this is going to be changed, because at that time this is your EA minus EB. So, there is a 3 phases in complete one cycle. Once it is conducting, then voltage will be 0. Once this is conducting, then this voltage is appearing here, means this voltage is same. So, this minus means EA minus EC will be appearing. Once this is conducting, then this EB is coming here, and EB means EA minus EB. So, the voltage across valve 1 at certain period it is your 0 once it is conducting, and if it is in off condition, it is nothing but your EA minus EB. Another terminology is used, that is called commutation voltage. The commutation voltage is the voltage at which the valve is going to be fired. You know, as I said, the valve 3 is conducting, because we are talking in the sequence of the conduction, means before 1, 3 was conducting. So, it is 3, 1, 2, 3, 1, 2, 3 and so on. So, forth, it is a sequence of conduction, means once here we will see the 3 was conducting, the voltage across this will be positive, then this can be fired, and it can be fired when this is going to be equal, EA is equal to your EC. So, in that wave shape I said that is here, it is going to be here, this is the conducting. So, this is called EAC, is called its commutation voltage, because it is going to be fired, means the voltage which is going to be just here going to be positive, so that it can be fired, means once your EAC becomes positive, if you will see from this graph again, because these things will be using when we will go for the bridge converter. Now, here as I said, we are taking as here 0 axis, means EC is coming output voltage, means your this valve 3 is conducting. So, your current was flowing from EAC to neutral in that previous diagram. Here now at this point this EA becoming positive compared to this EC means EA minus EC here is 0, and this EAC is called the commutation voltage of valve 1. Similarly, if you will see the commutation voltage of valve 2, it is you will see here means it is your EB minus EA, means this it is going to be positive. This commutation voltage is very important when we will go for the bridge circuit analysis, and the commutation voltage is the voltage when it is going to be positive, that valve can be fired, means can ignite, can be on, and as I said the V1 can be on when your EAC is going to be positive. So, at 0 instant it can be fired, and then it will be the, that is why the commutation voltage in this case for valve 1 it is this minus this, that is EAC. Similarly, for valve 2 it is your EBA, for this valve 3 it is EC minus EB, that is ECB. So, these are the commutation voltages, and you know is you see in one of the cycle here this is there is the 3 pulses. So, we are getting the 3 pulse cycle. Now, your pulses now it is your P is equal to 3 in this in one cycle. So, it is a 3 pulse 3 phase rectifier circuit, and the simple it is called one way circuit, 3 phase one way, because always it is one way, it is current is not flowing through those two. Now, if we will see the voltage across the peak inverse voltage, here once is going to be EAC is going to be positive here, means it is conducting. During these phases your 1 is off during this and this conduction phase, because only it is during this phase it is 1 is conducting, means once it is here this is your EAC up to this period. Now, here once the 2 is going to be on, now the voltage which is appearing in this circuit, again you can see how much voltage we are going to get. Now, once this was conducting, it was 0. Now, the next turn of this valve, we are assuming that we are giving the pulses at the regular interval. It is not that you are just off. We are assuming this is a continuous pulsation, it is every, these are 3 valves are there, means every it is in 1 pi 60 360 degree, it is 120 it is conducting. So, this 120 it is conducting, after that this is the turn and it is going to be fired. Once it is going to conduct, you can see the EB is appearing here, this is again off. So, the voltage here it will not come this side because this is off. So, the voltage across this will be your EB, and this is EA minus EB will be appearing across this. Similarly, the voltage across the valve 3 will be, this is the B here and this is EC. So, this minus this means EC minus EB will be appearing across the valve 3. Now, next turn is this. So, there will be sudden change, because from here to here we are going to this third is going to be fired, because the positive voltage arise after 120 degree again. So, the 3 will come here, the voltage across this becomes EA minus EC now, if it is a conducting. The voltage across this becomes EB minus EC. So, if you will see in our wave shape, the voltage you can see here, as I said here, once your 2 is conducting, the voltage across valve 1 here at this point itself, it was conducting here, it was 0, voltage across valve 1, suddenly this valve 2 is going to conduct here, now it is following this circuit here EAB, because EA is the positive side and B is coming here the cathode side. So, this voltage is going to follow here up to this point when third is going to be fired, because this EC is going to be positive than your EB. So, we can this valve will conduct. Now, at this point it is going to be EA minus EC, because EA was appearing at the anode side and cathode C is going to be, means third valve is conducting. Now, it is going to be here, and again we are following this. So, the peak inverse voltage in this case it is a EAB, it is not EA, means your EA in this case I can say here it is EM cos omega t or sin omega t here, let us suppose take. So, this is your line to line voltage. if your phase voltage here is your EM, then this voltage will be your line to line. In 3-phase circuit, it will be under root 3 multiplied by EM. So, the peak inverse voltage in this case, it is your under root 3 EM. So, this is, and you will find this is the valve 1 voltage we have drawn. Similarly, you can draw the voltage for valve 2, valve 3. It will be nothing but it will be slightly shifted 120 degree, because once this is a conducting, so this will be here, it will be conducting, and for the remaining period it will be similar shape. The current you can see, if for the valve 1, it is once it is conducting only for 120 degree, for here 120 and 120 it is off. So, this we are getting this current in the phase 1. Similarly, we are getting here for valve 2 conduction, it is this, and it is valve 3. If you add here all together, this is basically shows 3 1 2 3 1, it is nothing but it is the sequence of conduction. So, means you can see 1 is conducting, the current here is a DC across this, the voltage across this is a valve is 0, and the output voltage will be EA, because we are taking neutral as the return path. And if you see the primary current here, it is just like a pulses here that is appearing across the delta winding. But in this case, you will find this is the average value is not, average value is 0, but it is not a perfect sinusoidal in the phase. But if you convert into the delta side to the transformer of the here the line side, just I want to explain that here this is the this phase current we are talking. Now, if we will go for this current here, it will be this current minus this current will be this current, and then we will have the square wave or the output, and that we can see on the next term as well. So, here in this analysis you will see what we are getting. Now, here the each valve is conducting for 120 degree. The peak inverse voltage becomes, it is under 3 times of the phase voltage magnitude, and again it is always negative, because peak inverse voltage means inverse side of the voltage, and the current, this valve is carrying the current for only 120 degree, and the remaining 240 degree it is off condition. The phase here, the current of this delta winding, here we are getting this one, you can see we are getting here. If your transformer is star star, then what we are going to get, whatever the current here it is flowing, that will be in your the primary side, because in star star this is a valve is one phase current, it will be just transferred to the primary. But in the due to the delta here, we are getting the different shape current. You can see this current is no doubt the magnitude is less, but it is for wider 240 degree, and here it is for lesser degree. And due to this, again we are having our transformer is not utilized properly. In this case, you can say the transformer is only in the primary side, it is only conducting the primary winding, it is 120 degree, remaining time this one phase is idle, and only this here you can say 120 degree this and 120 degree this. So, the utilization of transformer, if you analyze, it is not proper, and also here it is giving some DC current that is appearing in your secondary side, and that is not true, because the DC current, which is, if you say take the average of any of the phases in the secondary side, it is a DC, and due to the again the DC current, it is not desirable in the transformer. So, here I want to tell that this is one very rough analysis of the 3-phase one-way circuit, but it is not used because it has so many limitations. Limitations, as I said, the DC current is appearing in your secondary, and also it is not properly utilized, but here the peak inverse voltage is not double, even though compared to other it is still less. And the power, we can also calculate what will be the power of the valve. It will be the average of this current multiplied by the peak inverse voltage. So, you can calculate what will be the valve rating. Valve rating in terms of voltage, it will be is under 3 em. The average current here, it will be how much? ID by 3, because the remaining period here is ID by 3, and if you are multiplying here, you are going to get, you see, is 1 by root 3 em ID by under root 3. And but this case, if we will take the average here, the DC is here average 0, but this is this phase is for this period it is less magnitude, but for constant more distance. Means more distance means 240, 120 and 120 degree. Here it is taking more current for this. So, your transformer is not symmetrically loaded, I can say, and that is why a proper care should be taken for this. So, I can just conclude the end of this lecture 1 that we analyze a very simple circuit starting from the half wave single phase rectifier circuit, and we saw about the rating of valves. We also saw what will be the valve voltages. We also saw what will be the DC instantaneous output voltage, and we calculated the average DC output as well. Then we saw a three phase one way circuit where it was a delta star transformer and the 3 valves were there, and then we saw the peak inverse voltage is under 3 times of peak sinusoidal magnitude, and then it is we also saw the DC currents are available in your secondary side, and the transformer is not properly utilized. Now, we will see some more 3 phase circuits. Then we will go for the actual requirement, what should be the desired features for our HVDC link converters, and then we will analyze in terms of general derivation. Here we derived for individual cases. Now, we have to derive a general expression, and then based on that we have to derive what should be the real configuration is required, and that will be discussed in your next lecture. Thank you.